Everything you are about to learn was discovered by people who did not want to believe it. The physicists who built quantum mechanics were not radicals looking to overturn reality. They were careful, conservative scientists trying to solve a few small problems left over from classical physics. What they found instead broke the world open, and several of them spent the rest of their lives trying to argue it away. They failed. The theory was right, and they knew it. Consider what that theory actually claims. A single particle can pass through two openings at once. It can be in many places until the instant you check, and then, only then, settle into one. Two particles can be linked so completely that measuring one decides the fate of the other, even if they sit on opposite ends of the universe. None of this is metaphor. These are measured results, repeated in laboratories for 100 years, accurate to a precision no other theory in science can match. That is the strange part. Quantum mechanics is not some fragile idea clinging to the edge of physics. It is the most successful theory we have ever produced. Your phone, the sun's light, the chemistry keeping you alive, all of it runs on rules that should not make sense, and yet do. So we are left with a serious question. If the theory works this well, and the world it describes looks nothing like the one we see, then which one is real? Over the next chapters, we will follow that question as far as the evidence allows, from the cracks in classical physics to the edge where space itself begins to dissolve. The first cracks did not look like cracks at all. At the end of the 19th century, physics seemed nearly complete. Newton's laws described the motion of everything from falling apples to orbiting planets with extraordinary precision. James Clerk Maxwell had unified electricity and magnetism into a single elegant framework, and his equations predicted that light itself was an electromagnetic wave traveling through space. Thermodynamics explained heat, energy, and the behavior of gases. The machinery of the physical world appeared to be understood, and many respected scientists believed that the remaining work amounted to little more than measuring known quantities to a few more decimal places. There is a famous sentiment from that era, often attributed to the leading physicists of the day, that the great discoveries were behind us and only refinement remained. It was one of the most confident moments in the history of science, and it was about to be undone by a handful of stubborn experiments that refused to behave. The trouble began with something as ordinary as the glow of hot objects. Heat a piece of iron, and it first turns a dull red, then orange, then a brilliant yellow-white as it grows hotter. Every solid object emits light when warmed, and the color of that light shifts in a predictable way with temperature. Physicists wanted to describe this glow precisely. They imagined an idealized object that absorbs all light falling on it and re-emits energy purely according to its temperature, a so-called blackbody, and they set out to calculate exactly how much light it should give off at each color, or more precisely at each wavelength. This seemed like a routine problem, the kind classical physics had solved 100 times before. Instead, it produced an answer so wrong that it became known as a catastrophe. When physicists applied the established rules of thermodynamics and electromagnetism to the problem, the mathematics made a clear prediction. A warm object should emit a modest amount of light at long wavelengths in the red and infrared, and then increasingly more energy at shorter wavelengths, climbing without limit toward the violet end of the spectrum and beyond. According to the equations, the amount of energy radiated at the shortest wavelengths should rise toward infinity. This was obviously absurd. It would mean that every warm object, including the human body, should be flooding its surroundings with an infinite burst of high-energy radiation. Open an oven door, and you would be met not with gentle warmth, but with a lethal blast of ultraviolet light. Since this plainly does not happen, something in the supposedly complete framework of classical physics was badly broken. The disagreement between theory and reality at short wavelengths was so severe that it earned the name the ultraviolet catastrophe, and it sat at the center of physics like a splinter no one could remove. The resolution came in 1900 from a German physicist named Max Planck, and it is worth understanding both what he did and how reluctantly he did it. Planck was a deeply traditional scientist, devoted to the classical physics he had grown up with. He did not set out to start a revolution. He was simply trying to find a formula that matched the experimental measurements of blackbody radiation, which by then had been recorded with great care. After much effort, he found a mathematical expression that fit the data perfectly across all wavelengths. But to derive that expression from first principles, he had to make an assumption that troubled him. He had to suppose that the energy emitted and absorbed by the vibrating particles in the blackbody did not flow continuously, as every physicist assumed it must, but came only in discrete amounts, small indivisible packets of a fixed size. Energy, in Planck's reluctant proposal, was not a smooth quantity that could take any value. It was grainy, delivered in lumps. The size of these lumps depended on the frequency of the light. Higher frequency radiation came in larger energy packets, lower frequency radiation in smaller ones, the two linked by a tiny number that would come to be called Planck's constant. This single assumption solved the catastrophe completely. At short wavelengths, the energy packets were so large that there was rarely enough thermal energy available to emit even one of them, which suppressed the radiation that classical physics had predicted would run to infinity. The grainy nature of energy acted as a natural break on the high-frequency end of the spectrum, and the curve bent back down to match exactly what was observed in the laboratory. The fit was flawless. Planck himself regarded the idea as a mathematical trick, a temporary device he hoped would eventually be explained away by some deeper continuous mechanism. He spent years trying to reconcile his packets of energy with the classical physics he trusted, and he never fully succeeded because there was nothing to reconcile. The graininess was real. What Planck had stumbled onto, almost against his will, was the first hint that the smooth, continuous world described by classical physics was an illusion produced by our coarse human scale. Underneath it lay a reality built from discrete units, a reality where certain quantities simply could not be divided below a minimum size. He had found the bottom of a staircase that everyone had assumed was a ramp. For a few years, Planck's discovery remained an isolated curiosity, a clever fix for one specific problem rather than a sign of anything larger. That changed in 1905, when a young patent clerk in Switzerland took the idea far more seriously than its own inventor had. Albert Einstein was examining a different puzzle, one involving light and metal, and he made a bold decision. Rather than treating Planck's energy packets as a mathematical convenience, he proposed that they were physically real, that light itself actually traveled through space as a stream of discrete bundles of energy. This was a far more radical claim, and it would force physics to confront a contradiction it had thought was already settled. The puzzle Einstein chose to solve concerned what happens when light strikes a metal surface, and the answer it gave would shatter the comfortable picture of light as a simple wave. To see why, we have to look closely at one of the most consequential experiments of the era, and at the strange behavior of light when it meets matter. The experiment in question was deceptively simple. Shine light on a clean metal surface, and under the right conditions, the metal will eject electrons. This is called the photoelectric effect, and by the early 20th century, it had been studied carefully enough that its details were well known. Those details, however, made no sense. Light was understood to be a wave, thanks to Maxwell's work and a century of supporting evidence. A wave carries energy spread across its entire front, and the energy it delivers should depend on its intensity. Shine a brighter light on the metal, deliver more energy, and the ejected electrons should fly out faster. Shine a dim light, and the electrons should crawl out weakly, or perhaps wait a while as they slowly absorbed enough energy to escape. That is what the wave picture demanded, and every physicist expected the experiments to confirm it. They did not. What the experiments showed was a set of stubborn facts that the wave theory could not explain. First, whether an electron was ejected at all depended not on the brightness of the light but on its color, which is to say its frequency. Red light, no matter how intense, could fail to free a single electron from a particular metal, while faint violet light would liberate electrons immediately. There appeared to be a threshold frequency, a kind of cutoff below which nothing happened regardless of how much light you poured onto the surface. Second, When electrons were ejected, increasing the brightness of the light increased the number of electrons, but not their individual energy. Brighter light of the same color produced more electrons, each moving at the same speed as before. To make the electrons themselves faster, you had to increase the frequency of the light, shifting it toward the blue and violet end of the spectrum. Third, the ejection happened essentially instantly, even for very dim light, with none of the delay the wave picture predicted, while electrons gradually soaked up energy. These results were genuinely baffling within the classical framework. A faint violet beam carries less total energy than a brilliant red one, yet only the violet beam could free electrons. Energy alone was clearly not the deciding factor. Something about the color of the light, its frequency, was doing the work, and the smooth wave model offered no reason why frequency should matter so decisively, while intensity barely mattered at all. This is the knot Einstein untied, and he did it by abandoning the assumption everyone else clung to. Einstein proposed that light is not a continuous wave delivering energy smoothly, but a stream of discrete packets, each carrying a fixed amount of energy determined entirely by the light's frequency. A particle of violet light carries more energy than a particle of red light because energy and frequency are tied together by exactly the relationship Planck had introduced. These packets would later be called photons. With this single idea, the entire puzzle dissolved. An electron is freed from the metal when a single photon strikes it and hands over its energy in one transaction. If that photon carries enough energy, which is to say if the light's frequency is high enough, the electron escapes. If the photon carries too little, as with red light below the threshold, the electron stays put no matter how many such photons arrive, because each interaction is a separate one-on-one encounter, and no electron is collecting energy from many photons at once. Increasing the brightness simply means sending more photons, which frees more electrons, but does nothing to change the energy any single photon delivers. And because each ejection is a single instantaneous event rather than a slow accumulation, there is no delay. Every strange feature of the experiment followed naturally from treating light as particles. This was a stunning resolution, but it carried a heavy cost. Light had been proven to be a wave definitively by experiments that no one doubted. Now Einstein was insisting it was a stream of particles. Both pictures had overwhelming evidence behind them, and both could not be simply true in the ordinary sense. The wave nature of light was not some loose interpretation that could be discarded. It rested on more than a century of precise observation, and to understand why physicists were so reluctant to give it up, we need to look at the experiment that had seemingly settled the matter long before Einstein was born. That experiment was performed around 1803 by an English polymath named Thomas Young, and it remains one of the most important demonstrations in all of physics. Young directed light through two narrow parallel slits cut close together in a barrier, and he let the light that passed through fall onto a screen behind. If light were a stream of simple particles, you would expect to see two bright bands on the screen, one behind each slit where the particles landed. Instead, Young saw something entirely different. The screen showed a series of alternating bright and dark bands spread across a wide region, a pattern of many stripes rather than two. This is the signature of waves, and to understand it, you only need to think about water. Imagine dropping two stones into a still pond at the same time. From each point of impact, ripples spread outward in expanding circles. Where the ripples meet, they interact. In some places, the crest of one wave arrives together with the crest of the other, and they add up to make a larger crest. In other places, the crest of one wave meets the trough of the other, and they cancel, leaving the water flat. This adding and canceling is called interference, and it produces a characteristic pattern of reinforcement and cancellation spreading across the surface. Young realized that the bright and dark bands on his screen were exactly this kind of interference pattern written in light. The bright bands appeared where waves from the two slits arrived in step and reinforced each other. The dark bands appeared where they arrived out of step and canceled. Particles cannot do this. Two streams of particles can only add together, never cancel. The dark bands, places where light plus light produces darkness, are impossible for particles and inevitable for waves. Young's experiment was therefore regarded as decisive proof that light is a wave, and for 100 years the matter was considered closed. This is the wall Einstein's photons ran into. The double-slit experiment showed beyond reasonable doubt that light interferes like a wave. The photoelectric effect showed, just as convincingly, that light delivers its energy in discrete particle-like packets. The evidence on both sides was solid. Light was not behaving like a wave or like a particle. It was somehow behaving like both, revealing one face or the other depending on what question the experiment asked. Physicists began to call this wave-particle duality, though naming it did little to ease the discomfort. It is one thing to give a contradiction a label and quite another to understand how nature could possibly accommodate it. The deeper unease came from a simple realization. If light, long thought to be a pure wave, also behaves like a particle, then the neat division between waves and particles that underlay all of physics was no longer reliable. Perhaps the categories themselves were the problem. Perhaps the universe was not built from things that are cleanly one or the other. And if that boundary could blur for light, a thoughtful person might begin to wonder whether it could blur in the other direction as well. Light was supposed to be a wave, and turned out to also be a particle. What about the things everyone was certain were particles, the solid little grains of matter like electrons, the building blocks of atoms? Could they, against all intuition, also have a wave hiding inside them? That question would soon be asked in earnest, and the answer would extend the strangeness from light into the very substance of the material world. Before we follow that question into the heart of matter, we need to understand why energy comes in packets at all, because the graininess Planck discovered runs deeper than the glow of warm objects. It shapes the structure of every atom, and it explains something that classical physics could not account for: why atoms exist as stable objects rather than collapsing in an instant. This is where the quantum leap gets its name, and it begins with a problem that should have destroyed the entire idea of the atom. By the early 20th century, physicists had a rough picture of the atom as a tiny, dense nucleus surrounded by electrons. The natural assumption, drawn directly from the success of Newton's mechanics in the orbits of planets, was that the electrons circled the nucleus the way Earth circles the Sun, held in their paths by electrical attraction in place of gravity. It was an appealing image, familiar and orderly. It was also catastrophically unstable, and Maxwell's own equations said so. According to the established laws of electromagnetism, any electric charge that accelerates must radiate energy in the form of electromagnetic waves. An electron moving in a circle is constantly accelerating because its direction is always changing, even if its speed is not. Such an electron should therefore be pouring out radiation continuously, bleeding away its energy. As it lost energy, it would spiral inward, faster and faster, until it crashed into the nucleus. The calculation was not vague. It predicted that every atom in the universe should collapse in a small fraction of a second, far less than the blink of an eye. Matter, by the rules of classical physics, should not be able to hold itself together at all. Yet, atoms are extraordinarily stable. The atoms in your body have persisted for billions of years, forged in ancient stars and carried across the galaxy without collapsing. Something was keeping the electrons from spiraling in, and classical physics had no idea what. There was a second clue lying alongside this one, equally unexplained. When elements are heated until they glow, or when an electric current is passed through a gas, they emit light. But they do not emit all colors. Each element gives off light only at a specific set of distinct, sharp wavelengths, a fixed pattern unique to that element, like a barcode written in color. Heat hydrogen, and it produces a particular red line, a blue-green line, and a few others at precise positions and nothing in between. Heat sodium, and it glows with the characteristic yellow that you see in older street lamps. These patterns are called spectral lines, and they are perfectly reproducible. Every hydrogen atom in the universe emits the same set of lines. Classical physics offered no explanation for why atoms should emit only these particular colors and not the smooth, continuous rainbow that a spiraling electron would produce. The Danish physicist Niels Bohr brought these two mysteries together in 1913 with a proposal as bold as it was strange. He suggested that the electrons in an atom could not occupy just any orbit. Instead, they were restricted to a specific set of allowed orbits, each at a fixed distance from the nucleus, and each corresponding to a particular, definite amount of energy. An electron could exist in one of these allowed states, but it could not exist anywhere in between. The spaces between the allowed orbits were simply forbidden, off-limits in a way that had no parallel in classical physics. While an electron sat in one of these special orbits, Bohr declared, it would not radiate energy at all, despite what Maxwell's equations demanded. It would simply remain there, stable, indefinitely. This was less an explanation than a decree, a rule imposed to match reality, but it worked, and its consequences were remarkable. In Bohr's picture, an electron could move from one allowed orbit to another, but only by jumping directly from one to the next, without passing through the space between. When an electron dropped from a higher energy orbit to a lower energy one, it had to shed the difference in energy, and it did so by emitting a single photon carrying exactly that amount of energy. Because the orbits had fixed energies, the gaps between them were fixed too, and so the emitted photons could only carry certain specific amounts of energy, which meant they could only have certain specific frequencies, which meant they could only appear as certain specific colors. The spectral lines were the fingerprints of these jumps. Each sharp line of color corresponded to an electron falling from one particular orbit to another, releasing a photon of one particular energy. The reason atoms emit only certain colors is that electrons can only occupy certain energy levels, and the reason they can only occupy certain energy levels is the same graininess that Planck had found in the glow of warm objects. The discreteness was everywhere, woven into the structure of matter itself. This is the origin of the phrase that has since drifted into everyday speech, usually misused. A quantum leap in ordinary conversation means a large and dramatic advance. In physics, it means almost the opposite. It is the smallest possible change an atom can make, an electron moving from one allowed state to the next with nothing in between. The leap is not large at all. What makes it remarkable is that it is abrupt and indivisible, a transition with no intermediate steps. The electron is in one orbit, then it is in another, and there is no meaningful sense in which it passed through the territory between them. This discontinuity is one of the defining features of the quantum world. Change at this scale does not flow smoothly. It happens in steps, in jumps, in discrete events separated by gaps that nature does not permit anything to occupy. Bohr's model was a triumph for hydrogen. It predicted the precise wavelengths of hydrogen's spectral lines with stunning accuracy, calculating from first principles the exact pattern that had previously been merely measured and catalogued. For the simplest atom, the agreement between theory and experiment was nearly perfect, and it convinced physicists that Bohr had captured something true about the structure of atoms. But the model had clear limits. It worked beautifully for hydrogen, with its single electron, and stumbled badly for atoms with more electrons. It also rested on assumptions that Bohr could not justify. Why were only certain orbits allowed? Why did an electron in an allowed orbit refuse to radiate in flat contradiction to electromagnetic theory? Bohr had no answer. He had found rules that worked, the way Planck had found a formula that worked, but the rules sat there unexplained, like commandments handed down without reasons. The discreteness was clearly real, confirmed by the spectral lines of every element, but its source remained hidden. There was a sense, growing among the physicists of the time, that these scattered discoveries were fragments of some larger structure not yet visible. Planck's energy packets, Einstein's photons, Bohr's allowed orbits, the graininess that kept appearing in one phenomenon after another. Each was a rule that fit the facts, and none was derived from any deeper principle. The theory of the quantum, such as it was, amounted to a collection of clever patches stitched over the wounds in classical physics. It described what happened without explaining why. A real theory, a coherent foundation from which all these rules would emerge naturally, did not yet exist, and the clue that would eventually point toward it came not from studying light or atoms directly, but from a young French aristocrat asking a question that sounded almost frivolous. If light, which everyone knew was a wave, could behave like a particle, then why should the reverse not also be true? Why should an electron, which everyone knew was a particle, not behave like a wave? It was a simple inversion of Einstein's idea, and it would crack the problem open. The young Frenchman was Louis de Broglie, and in 1924 he put this question forward in his doctoral thesis. The idea was almost unreasonably simple, which is part of what made it powerful. Einstein had shown that light, long regarded as a pure wave, also carries momentum and energy in discrete particle-like packets. De Broglie reasoned by symmetry. Nature tends toward balance, and if one of the two great categories, waves and particles, could trespass into the other's territory, perhaps the boundary was not a wall at all, but a fiction. He proposed that every particle of matter has a wavelength associated with it, determined by its momentum. A fast, heavy particle would have a very short wavelength. A slow, light particle would have a longer one. The relationship he wrote down tied the wavelength of any object directly to its momentum through Planck's constant, the same tiny number that kept surfacing wherever the quantum world revealed itself. At first glance, the proposal seemed to invite an obvious objection. If matter has a wavelength, why has no one ever seen a baseball or a person behave like a wave? The answer lies in the size of Planck's constant, which is almost inconceivably small. For any object of everyday size and speed, the wavelength that de Broglie's relationship produces is so minuscule that it is utterly undetectable, far smaller than an atomic nucleus, far smaller than anything that could ever be measured. A thrown baseball does have a wavelength in this sense, but it is so many times smaller than the ball itself that it has no observable consequences whatsoever. The wave nature of matter is hidden from us in daily life, not because it is absent, but because our scale is so enormous compared to the scale at which it operates. It is only when we descend to the realm of electrons and atoms, objects with tiny masses moving in confined spaces, that the wavelength grows large enough relative to the system to matter. For an electron inside an atom, the de Broglie wavelength is comparable to the size of the atom itself, and at that point the wave nature can no longer be ignored. This insight did something that Bohr's model had failed to do. It explained, rather than merely asserted, why electrons in atoms are restricted to certain orbits. Think of a guitar string fixed at both ends. When you pluck it, it does not vibrate in just any pattern. It can only vibrate in specific shapes where a whole number of half waves fits exactly between the two fixed ends. These are the standing waves, the natural modes of the string, and they are why a string produces certain definite musical notes rather than a continuous smear of sound. A pattern that did not fit evenly, that left a fractional wave hanging at the end, would interfere with itself and quickly die out. Only the patterns that close on themselves survive. De Broglie applied the same logic to the electron. If the electron is a wave wrapped around the nucleus, then only certain orbits will work, namely those whose circumference holds a whole number of electron wavelengths. An orbit where the wave fit perfectly, returning to its starting point in step with itself, would be stable. An orbit where it did not fit would have the wave interfere with itself destructively and cancel out, making that orbit impossible. The allowed orbits of Bohr's model were simply the orbits where the electron's wave forms a closed standing pattern. The mysterious quantization that Bohr had imposed by decree fell out naturally from treating the electron as a wave. The graininess was not arbitrary. It was the discreteness of musical notes, the same reason a flute plays distinct pitches rather than a continuous slide. This was a beautiful idea, but physics does not accept beauty as evidence. De Broglie's proposal made a concrete, testable prediction. If electrons are waves, then a beam of electrons should produce interference patterns, the same telltale bands of reinforcement and cancellation that proved light was a wave in Young's double-slit experiment. Electrons should be able to diffract, to spread and overlap and interfere in a way that no stream of simple particles ever could. The test came a few years later, around 1927, in two independent experiments. In the United States, Clinton Davison and Lester Germer fired a beam of electrons at a crystal of nickel. The regularly spaced atoms in the crystal acted like a grid of closely spaced slits, and the electrons bouncing off them produced a pattern of peaks and troughs in intensity at specific angles, exactly the diffraction pattern that waves would create and that the de Broglie wavelength predicted. Around the same time, George Paget Thomson achieved a similar result by sending electrons through thin metal foils and capturing the rings of an interference pattern on a screen behind. The electrons were behaving like waves. The prediction held precisely and quantitatively. Matter had a wave nature, and it was now an experimental fact rather than a philosophical speculation. There is a detail in this story worth pausing on because it captures the strangeness of the situation perfectly. George Paget Thomson, who proved that the electron behaves like a wave, was the son of Joseph John Thomson, who decades earlier had discovered the electron and demonstrated that it behaves like a particle. The father had shown the electron to be a tiny grain of matter with a definite charge and mass. The son showed the same electron to be a wave capable of interference. Both received the highest honors of their profession for their work, and both were correct. The electron is a particle, and the electron is a wave, and there's no contradiction once you accept that these are human categories the electron was never obligated to respect. The duality that Einstein had revealed for light was now confirmed for matter. Everything in the universe, light and substance alike, carries this double character. The consequences run far deeper than they might first appear, because once you accept that matter is wave-like, you have to ask what, exactly, is waving. For light, the wave was understood, at least classically, as an oscillation of electric and magnetic fields. But an electron is a single particle with a definite charge. When an electron behaves like a wave, what is it that spreads out, overlaps, and interferes? It is not the electron's matter physically smearing across space like spreading butter, because whenever you actually detect an electron, you find the whole thing in one place, a single compact particle, never a fraction of one. The wave is somehow associated with the electron without being made of the electron's substance. This question, which sounds almost like wordplay, turns out to be one of the most profound in all of physics, and the answer would redefine what physics is even able to describe. It would take the concrete, mechanical world of classical science and replace it with something far more abstract, a world described not by the positions of things, but by the spread of where things might be found. The technology that surrounds us was already quietly depending on these ideas before they were fully understood. The wave nature of electrons is not an obscure laboratory curiosity. It is the reason the electron microscope works, using the very short wavelength of fast-moving electrons to resolve details far finer than any beam of light could reveal, allowing us to see individual viruses and the arrangements of atoms in materials. It governs the behavior of electrons in metals and semiconductors and thus underlies the design of every transistor and every computer chip. The grainy, wave-like reality that Planck and Einstein and de Broglie uncovered is not a remote abstraction. It is the operating system of the material world, running silently beneath every solid surface you have ever touched. But to truly grasp how strange that operating system is, we need to return to the experiment that first revealed light's wave nature and perform it in a way Thomas Young never could have imagined. We need to send not a beam of many particles, but a single particle at a time, one after another, through those two slits, and watch what happens. What? Here is where the strangeness stops being a matter of categories and becomes something genuinely difficult to think about. The double-slit experiment, in its original form, used a beam containing countless particles of light all arriving together. And one could imagine the wave pattern emerging from the crowd, the many particles somehow jostling and arranging themselves into bands. That mental escape route seems reasonable until you close it off, and closing it off is exactly what modern versions of the experiment do. The technology now exists to send particles through the apparatus one at a time, with long pauses between them, so that each particle is utterly alone in its passage from source to screen. There is no crowd, there is no jostling. Each particle makes its journey in complete isolation, and only after a great many have passed do we examine the accumulated record of where they landed. What happens in this situation is the single most important fact in quantum mechanics, and more than any equation, it is the thing that tells us the universe is not what it seems. Begin with the version using electrons, since electrons are unambiguously particles in the everyday sense, with definite mass and charge, the very grains of matter that J.J. Thomson discovered. Set up a source that fires electrons one at a time toward a barrier with two narrow slits, and place behind the barrier a screen capable of recording the precise spot where each electron arrives. Fire the first electron. It passes through the apparatus and strikes the screen at a single definite point, leaving a small mark. This is exactly what a particle should do. It arrives as a whole, in one place, not spread out, not smeared, a single localized dot. So far, there's nothing troubling. Fire a second electron, and it too lands at a single point, somewhere else on the screen. A third, a fourth, each one a discrete dot in a seemingly random location. If you stopped after a handful of electrons, you would see a scattering of points with no obvious pattern, and you would feel confident that electrons are ordinary particles passing through one slit or the other and landing wherever they happen to go. But keep going. Fire hundreds of electrons, then thousands, then tens of thousands, always one at a time, always alone, and watch what the accumulating dots reveal. Slowly, out of what looked like randomness, a pattern emerges. The dots are not spread evenly across the screen, nor are they gathered into two clusters behind the two slits, as you would expect from particles each passing through one opening. Instead, they arrange themselves into a series of alternating bands, regions where many electrons landed separated by regions where almost none did. It is the interference pattern. It is the same pattern of bright and dark bands that Thomas Young saw with light, the unmistakable signature of waves reinforcing and canceling. Yet, every single electron arrived as a localized particle, one compact dot at a time, and no electron was ever in the apparatus alongside another. There was no crowd to interfere with. Each electron traveled alone, and yet the pattern that built up over many lonely journeys is the pattern of interference, the pattern that only waves can produce. Sit with what this requires. The interference pattern arises from waves passing through both slits at once and overlapping on the far side, the crest from one slit meeting the trough from the other to cancel, the crests meeting to reinforce. For this pattern to appear, something must be passing through both slits. But each electron is a single indivisible particle. It cannot split into two halves, one through each slit, because whenever an electron is detected, it is always whole, never fractional. And there was only ever one electron in the apparatus at any moment, so it could not have interfered with some other electron. The inescapable conclusion is that each individual electron, alone, somehow goes through both slits at once and interferes with itself. The wave that determines where the electron is likely to land passes through both openings, even though the electron, when finally detected, appears at a single point as a complete particle. The electron does not choose a slit. It explores both as a spread-out wave of possibility, and only when it strikes the screen and is detected does it become localized to one definite position. This is not a matter of our ignorance about which slit the electron really took. It is tempting to think the electron does pass through one slit or the other, and we simply do not know which, and the pattern is some statistical accident hiding that hidden truth. This comfortable interpretation can be tested, and it fails. If each electron genuinely went through just one slit, then blocking one slit should make no difference to the electrons that go through the other, and the pattern from one open slit plus the pattern from the other open slit should add up to the pattern with both slits open. They do not. With one slit open, you get a simple smear of electrons behind that slit, no bands. With the other slit open alone, the same. But with both slits open, you get the interference pattern, including dark bands at positions where, with a single slit open, electrons landed freely. There are places on the screen where an electron can arrive if only one slit is open, but where it can never arrive if both slits are open. Opening a second path, giving the electron more ways to reach a spot, somehow prevents it from reaching that spot at all. This is impossible for particles taking one route or the other. It is exactly what happens when waves from two sources cancel. The electron's two possible paths interfere, and the interference is real, with consequences you can see in the pattern on the screen. The same experiment has been performed not just with electrons, but with progressively larger objects, and the wave behavior persists in a way that erodes any hope that this is some special quirk of tiny fundamental particles. Whole atoms, far more massive and complex than electrons, produce the interference pattern when fired one at a time through a suitable double-slit arrangement. Molecules built from dozens, then hundreds, then thousands of atoms have been sent through versions of the experiment, and they too show the bands of interference, demonstrating that each large molecule passed through the apparatus as a spread-out wave, exploring multiple paths simultaneously before arriving as a single localized object. There is no known upper limit to this behavior, no point at which physicists have found the wave nature suddenly switching off. The difficulty in performing the experiment with ever larger objects is purely practical. Bigger objects have shorter wavelengths and interact more readily with their surroundings, which disturbs the delicate wave behavior, but the principle appears to hold all the way up. In the equations of quantum mechanics, there is nothing that says a cat or a person or a planet could not in principle show the same interference, given an apparatus inconceivably more precise than anything we could ever build. The wave nature is not a property of small things. It is a property of all things, made invisible at large scales only by the practical impossibility of isolating big objects well enough to reveal it. So we are left with a picture of reality that is difficult to reconcile with ordinary experience. Between the moment an electron leaves its source and the moment it strikes the screen, it does not have a definite path. It does not travel from here to there along a single line the way a thrown stone does. Instead, it propagates as a wave of possibilities, a spread-out something that passes through every available route at once, exploring all the ways it might go. Only at the moment of detection does it become a particle at a single location. The position the electron will be found at is not determined in advance. Before measurement, the electron does not have a position in the ordinary sense at all. It has a range of possible positions, each with a certain likelihood, encoded in the wave. The act of measuring forces the issue, compelling the spread-out possibility to resolve into one actual outcome. This raises a question that should make anyone uneasy, and it is the question that has haunted quantum mechanics since its inception. If the electron travels through both slits as a wave of possibilities and only becomes a definite particle when it is detected, then what happens if we try to catch it in the act? What if we place a detector at the slits themselves and simply watch to see which slit each electron passes through? The answer to that question is more disturbing than the pattern itself, and it forces us to confront the role of measurement in the most direct way possible. The experiment is straightforward to describe. Take the same double-slit setup, with electrons fired one at a time, but now install a small detector at each slit, a device that registers when an electron passes through it. The goal is simple curiosity. The electrons produce an interference pattern, which seems to require each electron to pass through both slits at once. Very well, let us watch and see how a single particle manages to go through both openings simultaneously. Let us catch the electron in the act of doing the impossible thing the pattern implies. We turn on the detectors, fire the electrons one by one, and record both which slit each electron went through and where it landed on the screen. What we find dismantles the picture we had just built, and it does so in a way that no one has ever fully explained. The moment the detectors are switched on and we begin recording which slit each electron passes through, the interference pattern disappears. It does not weaken or blur. It vanishes entirely, replaced by exactly what you would expect from ordinary particles, two simple bands of electrons gathered behind the two slits, with no alternating stripes, no dark cancellation bands, no sign of wave behavior at all. The electrons, when watched, behave like particles. Each one goes through one slit or the other. The detector duly registers which, and the electron lands behind the slit it actually traversed, building up over many trials into the two clusters that common sense always predicted. The wave nature is gone. And here's the part that defies easy explanation. Switch the detectors off, stop recording which slit each electron passes through, and the interference pattern returns immediately. The very same apparatus, the very same electrons, produce wave behavior when we do not look and particle behavior when we do. The only thing that changed is whether information about the path was obtained. This is the observer effect, and it is essential to be precise about what it does and does not mean, because it is among the most misunderstood results in all of science. The popular interpretation holds that human consciousness somehow reaches out and alters reality, that the universe behaves differently because a mind is paying attention, that awareness itself collapses the wave. This mystical reading has been attached to quantum mechanics for decades, and it is not supported by the physics. The detectors do not require a conscious human watching their output for the pattern to disappear. The interference vanishes whether or not anyone ever reads the record. What matters is not consciousness, but information, specifically whether the witch path information physically exists anywhere in the world. If the apparatus is arranged so that the path of the electron leaves a permanent mark, an irreversible physical record of which slit it went through, the interference is destroyed, regardless of whether any person ever examines that record. The electron's wave behavior depends on whether the universe, in effect, keeps track of which way it went. The reason for this lies in the nature of the wave itself, though the full explanation took physicists decades to develop and remains contested in its deepest interpretation. The interference pattern requires that the two possibilities, the electron going through the left slit and the electron going through the right slit, remain genuinely indistinguishable, blended together with no fact of the matter about which one actually occurred. As long as no record exists anywhere that could distinguish the two paths, they overlap and interfere, and the wave of possibility passes through both slits and produces the bands. But the instant a detector creates information about which path was taken, the two possibilities become distinguishable. There now exists a fact about which slit the electron went through, and once that fact exists, the two paths can no longer blend. The electron is forced to have gone through one slit or the other, and with the blending broken, there is nothing to interfere, and the pattern collapses into the two simple particle bands. The act of acquiring path information does not gently nudge the electron. It eliminates the very overlap of possibilities that the interference depended on. This is genuinely strange, and it should not be smoothed over. The behavior of the electron depends on whether information about its path is available, not on any physical force pushing it one way or another. You might suspect that the detector simply disturbs the electron, knocking it off course in the process of measuring it, and that this disturbance washes out the pattern. This was an early hope that the observer effect was just clumsy measurement, the equivalent of trying to feel a snowflake and melting it in the process. But cleverer versions of the experiment have ruled this out. It is possible to design path detectors so gentle that they impart almost no disturbance to the electron, and the interference still vanishes the moment which path information becomes available. Even more striking are arrangements where the path information is recorded but can be erased afterward. In these so-called quantum eraser experiments, if the witch path information is destroyed before the final measurement is complete, the interference pattern reappears, even though a detector did physically interact with the electron. The deciding factor is not the physical disturbance from measurement. It is whether, in the end, the information about which path was taken exists or does not exist. Reality at this level seems to care about information in a way that has no precedent anywhere in classical physics. These results force a question that physics has never comfortably answered. What counts as a measurement? What is special about the interaction between the electron and a detector that ends the wave behavior, when the electron has presumably been interacting with stray particles and fields throughout its journey without collapsing? Where exactly is the line between the quantum world, where possibilities spread out and interfere, and the classical world, where objects have definite properties and particles go through one slit or the other? The electron in flight is described by a spreading wave of possibilities. The mark on the screen is a definite single fact. Somewhere between the two, the possibilities became an actuality, the many became one. This transition, from a spread of potential outcomes to a single realized result, is the central mystery, and it does not appear anywhere in the equations that otherwise describe the quantum world with perfect accuracy. The mathematics tells us how the wave of possibilities evolves and spreads. It does not tell us how or why or when that wave of possibilities suddenly yields a single concrete result when a measurement is made. That gap in the theory has a name and a long history of argument, and it goes to the heart of what quantum mechanics is actually telling us about reality. There's a further subtlety that deepens the puzzle rather than resolving it. The electron does not merely fail to have a definite position before measurement. It also does not have many other definite properties. Its momentum, its energy, its spin, all of these can exist in the same blended indefinite state, a superposition of multiple values at once, until a measurement forces one of them to take a definite value. And crucially, measuring one property can leave others more uncertain than before. When you pin down precisely where an electron is, you lose the ability to say precisely how it is moving, and the reverse holds as well. There is a fundamental trade-off built into the act of measurement, a limit on how much can be known about a quantum system at one time. This limit is not a practical constraint that better instruments could overcome. It is woven into the structure of reality itself, a hard boundary that no measurement, however clever, can cross. Understanding why that boundary exists and what it reveals about the wave-like nature of matter is the next step in seeing just how different the quantum world is from the one our intuitions were built for. The boundary has a name. It is called the uncertainty principle, formulated by Werner Heisenberg in 1927, and it is one of the most widely cited and most thoroughly misunderstood ideas in all of science. The principle states that there are certain pairs of properties belonging to a particle that cannot both be known with perfect precision at the same time. The most famous such pair is position and momentum, where momentum is essentially the particle's mass multiplied by its velocity, a measure of how it is moving. The principle says that the more precisely you determine a particle's position, the less precisely its momentum can be known, and the more precisely you determine its momentum, the less you can say about its position. There is a strict mathematical limit on the product of the two uncertainties, set once again by Planck's constant, that same small number standing guard at every threshold of the quantum world. You cannot beat this limit. No experiment, no instrument, no technique, however ingenious, can pin down both quantities at once beyond what the principle allows. The common explanation of this principle is wrong, and the error is worth correcting carefully because it obscures something far more interesting than the usual story admits. The popular account says that to measure a particle's position, you have to bounce something off it, a photon of light, say, and this collision disturbs the particle and changes its momentum, so the act of measuring position necessarily ruins your knowledge of momentum. This sounds plausible, and Heisenberg himself initially described it this way, using a thought experiment about observing an electron with a microscope. But this disturbance story implies that the particle really does have a definite position and a definite momentum simultaneously, and that the uncertainty is merely a practical problem of measurement getting in the way, a limitation of our clumsy probing. That is not what the uncertainty principle means. The uncertainty is not a statement about the limits of measurement. It is a statement about the nature of the particle itself. A quantum particle does not possess a perfectly definite position and a perfectly definite momentum at the same time, even when no one is measuring it. The properties are not merely unknown. They are genuinely indefinite, not yet determined, simply not there as sharp values waiting to be uncovered. To see why this must be so, return to the wave nature of matter, because the uncertainty principle is not a separate mysterious rule bolted onto the theory. It is a direct and unavoidable consequence of the fact that particles are described by waves, and it follows from properties of waves that were understood long before quantum mechanics existed. Consider what it means for a wave to have a well-defined wavelength. A pure wavelength belongs to a wave that oscillates with the same regular rhythm over a long stretch, crest after crest after crest, evenly spaced, extending far across space. Such a wave has a very precise wavelength, but notice that it is spread out everywhere along its length. You cannot point to where this wave is because it is not anywhere in particular. It is distributed across a vast region. Now, in quantum mechanics, a particle's momentum is directly tied to its wavelength through de Broglie's relationship. A precise wavelength means a precise momentum, so a particle with a very precisely defined momentum corresponds to a wave spread out over a large region of space, which means its position is highly uncertain. The very thing that makes its momentum precise, the long, regular train of evenly spaced crests, is the thing that makes its position vague. Now consider the opposite extreme. Suppose you want a particle with a well-defined position, a wave concentrated in one small region so that you can say with confidence where the particle is. To build a wave that is sharply localized, bunched up in a single small spot and nearly flat everywhere else, you cannot use a single pure wavelength. A single wavelength spreads out forever. To make a localized lump, you have to add together many waves of different wavelengths, combining them so that they reinforce in one small region and cancel everywhere else. This is a standard mathematical fact about waves of every kind, true of sound and water and light, established well over a century before quantum theory. A localized pulse is necessarily built from a spread of different wavelengths, but each wavelength corresponds to a different momentum, so a wave that is sharply localized in position is necessarily composed of many different momenta blended together, which means its momentum is highly uncertain. The sharper the localization in position, the wider the range of wavelengths required to build it, and therefore the greater the spread in momentum. The trade-off is exact, and it is forced by the mathematics of waves themselves. This is the true origin of the uncertainty principle. It is not about clumsy measurement disturbing a delicate particle. It is about the simple fact that a wave cannot be both perfectly localized and possess a single, perfectly definite wavelength at the same time, because those are contradictory demands. Localization requires many wavelengths, a single wavelength forbids localization, and a particle that is fundamentally a wave inherits this trade-off as a basic feature of its existence. Position and momentum are linked through the wave the way a musical note's pitch and its duration are linked. A sound clipped to an instant has no well-defined pitch, while a sound with a perfectly pure pitch must ring on and on. You cannot have both a precise pitch and a precise instant, and you cannot have both a precise position and a precise momentum for fundamentally the same mathematical reason. The uncertainty is built into what it means to be a wave. The consequences of this reach into the structure of matter and the behavior of the vacuum in ways that are far from abstract. Consider why atoms have a definite size, why electrons do not simply spiral into the nucleus as classical physics predicted. The uncertainty principle provides a genuine answer where Bohr could only impose a rule. If an electron were to fall all the way into the tiny nucleus, its position would become extremely well-defined, confined to an exceedingly small region. But by the uncertainty principle, confining its position so tightly would force its momentum to become enormously uncertain, which means the electron would have to be moving extremely fast on average, carrying tremendous energy. This large kinetic energy resists the confinement and effectively pushes the electron back outward. The actual size of an atom represents a balance, a compromise between the electrical attraction pulling the electron toward the nucleus and the uncertainty principle resisting the confinement that would result. The atom is as small as it can be, without violating the trade-off between position and momentum, and not one bit smaller. The stability of matter, the simple fact that you do not collapse into a point, that the chair holds together, that anything has size at all, rests directly on this principle. Uncertainty is not a limitation, it is what holds the world up. The principle applies to other pairs of quantities as well, and one of them has consequences that reach into the nature of empty space itself. There is an uncertainty relationship between energy and time, structured the same way as the one between position and momentum. Over a very short interval of time, the energy of a system cannot be perfectly defined. The shorter the interval, the greater the uncertainty in energy. This sounds like a technicality, but it leads somewhere remarkable. It means that over sufficiently brief moments, energy can fluctuate, can be borrowed from nothing, and repaid before any measurement could ever catch the imbalance. In completely empty space, in a perfect vacuum with nothing in it at all, the energy is not fixed at zero. It cannot be, because a precisely defined energy over an extended time would itself violate the uncertainty relationship. Instead, the vacuum seethes with tiny fluctuations of energy, fleeting and constant, and these fluctuations can briefly give rise to particles that flicker into existence and vanish again before the cosmic books must balance. Empty space, it turns out, is not empty. It is a restless medium, and the uncertainty principle is the reason. But before we follow that thread into the structure of the vacuum, we need to confront the object at the very center of quantum mechanics, the thing that actually does the waving, the mathematical entity that holds all these possibilities and somehow governs a world that refuses to be definite until it is asked. That object is called the wave function, and it sits at the absolute center of quantum mechanics, the mathematical heart from which everything else follows. Erwin Schrödinger introduced it in 1926, writing down an equation that describes how it behaves and evolves over time. And that equation has since proven to be among the most successful in the history of physics, predicting the outcomes of countless experiments with flawless precision. Yet for all its success, the wave function remains deeply puzzling, because while we know exactly how to use it, physicists still argue about what it actually is. It is the tool that works perfectly, and the mystery that refuses to resolve, both at once, and understanding it is the key to understanding why the quantum world behaves as it does. Begin with what the wave function does, because that much is not in dispute. For any quantum system, an electron, an atom, a collection of particles, there is a wave function that contains everything the theory can possibly tell you about that system. It is a mathematical object spread through space, and it captures the spread of possibilities we have been circling around in every experiment so far. The wave function is the wave that passes through both slits. It is the spread-out cloud of potential positions an electron occupies before it is measured. It is the standing pattern wrapped around the nucleus that determines the allowed orbits. All the wave-like behavior of matter, all the interference, all the indefiniteness is encoded in this single object and in the equation that governs how it changes. Schrödinger's equation tells you, given the wave function now, exactly what the wave function will be at any future moment. And here is a crucial point that is often lost. Schrödinger's equation is perfectly smooth, continuous, and deterministic. The wave function evolves in a completely predictable way, flowing forward in time without any jumps, any randomness, any uncertainty whatsoever. Given the wave function at one instant, its entire future is fixed. The unpredictability of quantum mechanics does not live in the wave function's evolution. It lives somewhere else, and locating it precisely is part of the puzzle. The question then is what the wave function represents. What is this spread-out mathematical wave actually describing about the world? The answer came from Max Born, also in 1926, and it was an answer so strange that it changed the meaning of physical theory itself. Born proposed that the wave function does not directly tell you any physical quantity you can measure. Instead, it tells you probabilities. Specifically, the wave function at a given point in space, when squared in a particular mathematical sense, gives the probability of finding the particle at that point if you make a measurement. Where the wave function is large, the particle is likely to be found. Where it is small, the particle is unlikely to be found. Where it is zero, the particle will never be found. The interference pattern in the double-slit experiment is precisely a map of this probability. The bright bands marking where the wave function is large and electrons are likely to land. The dark bands marking where it is zero and no electron ever appears. The wave is a wave of probability, and its peaks and troughs are the peaks and troughs of likelihood. This was a profound break with everything physics had been before. For all of history, the goal of a physical theory had been to predict what will happen. Given the present state of a system, classical physics told you its future with certainty. Drop a stone, and Newton's laws tell you exactly where it will be at every instant. But the wave function does not do this. It does not tell you where the electron will be. It tells you only the probability of finding it in various places. Run the same experiment twice with the electron prepared in exactly the same way, the very same wave function, and the electron may land in different places on the screen each time. The outcome is not determined by the wave function. Only the probabilities of the various outcomes are determined. This means that at its deepest level, as far as quantum mechanics can tell us, the universe is not deterministic. Identical causes do not produce identical effects. Two electrons in identical states can do different things, and there is no hidden reason, nothing the theory can point to, that decides which one does what. Pure chance sits at the foundation of physical reality, or so the theory appears to say. This is what Einstein could not accept, and it produced one of the most famous objections in the history of science, usually paraphrased as his insistence that God does not play dice with the universe. Einstein did not doubt that quantum mechanics worked, that its predictions matched experiment. What he doubted was that it was complete. He believed that the apparent randomness must be a sign of our ignorance, that beneath the probabilistic wave function there must be some deeper layer of reality, some hidden details that, if we only knew them, would determine the outcome and restore the comforting certainty of classical physics. The electron, in Einstein's view, surely had a definite position all along, and the wave function's probabilities reflected merely our incomplete knowledge of those hidden details, the way a weather forecast gives probabilities, not because the weather is truly random, but because we lack complete information about the atmosphere. This was a reasonable position, perhaps the most reasonable position, and for decades it could not be tested. It seemed to be a matter of philosophy, of taste, of which kind of universe one preferred to believe in. Whether the randomness was fundamental or merely apparent looked like a question that experiment could never decide. We will see later that this assumption was wrong, that the question could be tested, and that the answer was not the one Einstein hoped for. But there is a more immediate and pressing problem with the wave function, one that does not wait for sophisticated experiments, and that confronts us the moment we ask how measurement works. The wave function spreads out, exploring many possibilities, the electron's probability distributed across a wide region through both slits over the whole screen. Then a measurement is made, and the electron is found at one definite spot. In that instant, the wave function appears to change abruptly and discontinuously. Before the measurement, it was spread out, assigning probability to many locations. After the measurement, the electron is definitely here, at this point, and nowhere else. So the wave function must now be concentrated entirely at this one location, having dropped to zero everywhere it previously had value. This sudden transformation from a spread-out wave of many possibilities to a sharp spike at a single realized location is called the collapse of the wave function. And it is a deeply troubling thing because nothing in Schrödinger's equation describes it or permits it. The equation, recall, is smooth and continuous and deterministic. It evolves the wave function gently, with no jumps. The collapse is a jump, an abrupt and random discontinuity, and it is simply not present in the mathematics that otherwise governs the wave function perfectly. We have a theory with two completely different rules. One rule, Schrödinger's equation, governs the wave function when no one is measuring it, and it is smooth, deterministic, and continuous. The other rule, the collapse, takes over when a measurement is made, and it is abrupt, random, and discontinuous. The theory does not say when to use which rule. It does not define what a measurement is. It does not explain how or why the collapse happens, or whether it happens at all. This is the measurement problem, and it is arguably the deepest unsolved problem in the foundations of physics, unresolved for nearly a century despite the efforts of the finest minds in the field. The wave function works. Use it, evolve it with Schrödinger's equation, square it to get probabilities, and you will predict the results of any experiment you like with breathtaking accuracy. But ask what it is. Ask what is really happening when a measurement collapses it. Ask where the smooth quantum world of spreading waves ends and the definite classical world of single outcomes begins, and the theory falls silent. The most successful framework in science cannot account for the most basic event in any experiment, the act of getting a definite result. To see just how strange this gap becomes, we can take the logic of superposition, the idea that a quantum system exists in many states at once until measured, and follow it upward, out of the realm of electrons and atoms into the world of ordinary objects. There is a thought experiment devised by Schrödinger himself that does exactly this, and it remains the sharpest illustration of how unsettling the measurement problem really is. Schrödinger devised his thought experiment in 1935, and notably, he did not intend it as a celebration of quantum strangeness, but as a criticism, a way of showing how absurd the theory became when its logic was followed to its natural conclusion. He wanted to expose a problem, not to mystify. The setup is deliberately constructed to take the indefiniteness of the quantum world, which we readily accept for electrons hidden from view, and connect it directly to the fate of something large and familiar, something whose state we cannot pretend to be indifferent about. The thought experiment has become so well known that its central image has escaped physics entirely and entered popular culture, usually stripped of the careful reasoning that gives it meaning. To understand what it actually shows, we need to build it up carefully, because the power of the argument lies entirely in the chain of logic connecting the very small to the very large. Imagine a sealed box and inside it a single radioactive atom. Radioactive decay is a genuinely quantum process. An unstable atom may decay, emitting a particle, or it may not, and quantum mechanics does not determine which will happen. It gives only a probability. Over some span of time, there might be an even chance that the atom has decayed and an even chance that it has not. Critically, before any measurement, the atom is not secretly in one state or the other. According to the theory we have been developing, the atom exists in a superposition, a blend of both possibilities at once, decayed and not decayed simultaneously, exactly as the electron passed through both slits at once. This is not a statement about our ignorance. It is the same indefiniteness that produces interference, the same spread of possibilities encoded in the wave function. For a single atom hidden in a box, this is strange but tolerable. We've already accepted that electrons and atoms behave this way. The genius of Schrödinger's construction is what he does next, which is to build a chain that amplifies this microscopic indefiniteness up to the scale of an object we cannot help but think of in definite terms. Inside the box, Schrödinger places a mechanism. A detector watches the atom, and if the atom decays, the detector triggers a device that releases a poison, which kills a cat that has also been placed inside the sealed box. If the atom does not decay, nothing happens. The poison is not released, and the cat remains alive. The box is sealed, isolated from the outside world, and no information about what is happening inside can escape. Now we apply the logic of quantum mechanics consistently, refusing to make any special exception for large objects, since the theory itself contains no such exception. The atom is in a superposition of decayed and not decayed. The detector is linked to the atom, so it enters a superposition of having triggered and not triggered. The poison mechanism is linked to the detector, so it enters a superposition of released and not released. And the cat, linked to all of this, enters a superposition of dead and alive. Following the mathematics of quantum mechanics strictly, with no arbitrary cutoff separating the quantum from the classical, the cat is not secretly alive or secretly dead while the box remains sealed. It is in a blended state of both, a superposition of a living cat and a dead cat, in exactly the same sense that the atom is a superposition of decayed and not decayed. Only when the box is opened and an observation is made does the wave function collapse, the superposition resolves, and the cat becomes definitely one or the other. This conclusion is meant to be unacceptable, and that is precisely the point. We have no difficulty imagining an electron spread across two slits, because an electron is alien to us and we have no strong intuition about what it should be doing. But a cat is a large, warm, breathing creature, and the idea that it could be genuinely suspended between life and death neither one nor the other, but a blend of both, strikes us as not merely strange, but meaningless. A cat is alive or it is dead. There is no third state, no smear between them, no superposition of a living animal and a corpse. Our intuition rebels, and Schrödinger intended exactly this rebellion. His argument runs as follows. The same quantum mechanics that works perfectly for atoms when applied without any special exception to large objects predicts that the cat should be in a superposition of dead and alive. Since this is absurd, something must be wrong or incomplete in our understanding of how quantum mechanics applies to ordinary objects. The thought experiment is a challenge, a demand that physics explain why the superpositions we accept for atoms do not seem to occur for cats, and where exactly the boundary lies. The challenge is sharp because it exposes the measurement problem with maximum clarity. If superposition is real for the atom and the cat's fate is rigidly tied to the atom's state, then by what principle does the superposition stop somewhere between the atom and the cat? At what point in the chain, the atom, the detector, the poison, the cat, does the blend of possibilities become a single definite fact? Quantum mechanics, as we have seen, does not specify what counts as a measurement, does not draw a line between the quantum realm where superpositions live and the classical realm of definite outcomes. The cat experiment forces this gap into the open. Somewhere, the spread-out wave of possibilities must become one actual result, but the theory does not say where or how or why. The cat is a magnifying glass held up to the crack in the foundation of physics, enlarging a microscopic ambiguity until it concerns the life of an animal and can no longer be ignored. Various responses to this challenge have been offered, and they correspond to different ways of understanding what quantum mechanics is really telling us. One response holds that the cat is never truly in a superposition of dead and alive, because the connection between the cat and the surrounding world is far too rich and complex to maintain such a delicate blend. This idea, developed more fully in later decades, is called decoherence, and it provides an important part of the answer. A single electron can be isolated well enough to remain in a clean superposition, exploring both slits, because it interacts with almost nothing on its way to the screen. But a cat is constantly interacting with everything around it, with countless air molecules, with photons of light, with the floor of the box, with its own internal heat radiating outward. Every one of these interactions carries away a trace of information about whether the cat is alive or dead, spreading that information into the environment almost instantly. The delicate superposition, which requires the two possibilities to remain perfectly blended and indistinguishable, cannot survive this onslaught of information leaking into the surroundings. The blend is destroyed in a fraction of an unimaginably small fraction of a second, far faster than any cat could exist in such a state. Decoherence explains why we never see large objects in obvious superpositions. They cannot be isolated well enough, and the moment they interact with their environment, the superposition is effectively dissolved into ordinary probabilities. But decoherence, important as it is, does not fully solve the measurement problem, and it is essential to be honest about this rather than papering over the gap. Decoherence explains why the superposition becomes practically impossible to observe in a large object, why the interference between the dead cat possibility and the alive cat possibility vanishes so quickly that it can never be detected. It explains why the cat appears, for all practical purposes, to be definitely one or the other. What it does not explain is why, in the end, there is a single actual outcome at all. Even after decoherence has scrambled the superposition beyond any hope of detection, the mathematics still contains both possibilities, the dead cat and the living cat, both still present in the wave function, merely no longer able to interfere. Something must still select which one is real, must still account for the fact that when we open the box, we find one definite cat and not a ghostly blend. Decoherence converts the strange quantum superposition into something that looks like ordinary classical probability, a simple either-or with definite odds. But it does not explain how the either-or becomes a single this. The deepest question remains. And so physicists have been driven to consider possibilities far stranger than a cat suspended between life and death, possibilities about the nature of reality itself that make the original thought experiment seem almost tame. One of these possibilities suggests that the cat really is both dead and alive, that nothing ever collapses at all, and that the resolution we experience is an illusion produced by our place within a far larger and stranger structure than we have ever imagined. Before we follow that radical possibility to its conclusion, we need to examine the feature of quantum mechanics that troubled Einstein more than any other, the one he spent years trying to use as a weapon against the theory, only to have it turn into the strongest confirmation that the quantum world is exactly as strange as it appears. This is entanglement, and it is the phenomenon that connects two particles so intimately that they can no longer be described separately, no matter how far apart they travel. Einstein found it so disturbing that he gave it a dismissive name, calling it spooky action at a distance, and he was convinced it revealed a flaw that would eventually bring the whole theory down. He was wrong, and the way he was proven wrong is one of the great stories in the history of science. To understand entanglement, we first need to extend the idea of superposition from one particle to two. We have seen that a single particle can exist in a blend of possibilities, an electron in a superposition of going through the left slit and the right slit, an atom in a superposition of decayed and not decayed. Now, consider two particles and a property called spin, which for our purposes can be thought of as a kind of orientation that, when measured along some direction, comes out as one of two possible results, which we can simply call up and down. A single particle can be in a superposition of spin up and spin down, indefinite until measured. But when two particles interact in the right way, something new becomes possible. They can be prepared in a joint state in which neither particle has a definite spin on its own, yet their spins are perfectly correlated. For instance, two particles can be created in a combined state where, whenever they are measured along the same direction, one will be found spin up and the other spin down, always opposite, with certainty, even though before the measurement, neither particle has any definite spin at all. The two particles do not each carry their own separate state. They share a single joint state that cannot be split into a description of one particle plus a description of the other. This is entanglement. The particles have become, in a precise mathematical sense, a single system, even if they are physically separated. Now, send these two entangled particles far apart, one to a laboratory here and the other carried across a great distance to another city, another planet, in principle to the far side of the galaxy. They remain entangled, their shared state intact, neither particle possessing a definite spin. Then, measure the spin of the first particle along some direction. Instantly, that particle's spin takes a definite value, say up. And in the very same instant, the distant second particle's spin becomes definite as well, taking the opposite value, down. Before the measurement, neither had a definite spin. The instant one is measured, both become definite, perfectly correlated, no matter how far apart they are. This is what Einstein found so objectionable. It seems as though measuring the first particle reaches across the intervening distance and forces the second particle to take a definite opposite value, faster than any signal could travel between them, faster than light. The correlation appears instantaneous, spanning any distance at once. To Einstein, who had established that nothing can travel faster than light, this looked like a fatal absurdity. Surely, he argued, the particles must have carried their definite spins with them all along, decided at the moment they were created and simply hidden from us until measured. The correlation would then be no more mysterious than a pair of gloves separated into two boxes. Open one box, find a left glove, and you know instantly the other box holds a right glove with no spooky influence required. The gloves were always left and right. We merely learned which was which. This was Einstein's proposal, developed in detail in 1935 together with two colleagues, Boris Podolsky and Nathan Rosen, in a paper that posed the problem as a sharp challenge. Either quantum mechanics is incomplete, they argued, missing some hidden information that the particles actually carry, or else nature permits this spooky instantaneous action across any distance, which they regarded as unacceptable. They were certain the resolution must be hidden information, that the particles were like the gloves, their properties fixed in advance and merely unknown to us. The wave function's failure to specify those properties would then reflect not a genuine indefiniteness in nature, but an incompleteness in the theory. Exactly the position Einstein held about quantum randomness in general. For nearly 30 years, this remained a matter of interpretation, seemingly beyond the reach of any experiment. Both views, the hidden information of Einstein and the genuine indefiniteness of standard quantum mechanics, predicted exactly the same correlations between the particles. There seemed to be no way to tell them apart, no measurement that could decide whether the particles carried hidden instructions or whether their properties truly came into being only upon measurement. The question looked permanently philosophical. Then, in 1964, a physicist named John Stuart Bell found something that no one had expected to exist. He discovered that the two views, hidden information versus genuine quantum indefiniteness, do not in fact always predict the same thing. They agree in the simple case where both particles are measured along the same direction, where both theories predict perfect correlation. But Bell realized that if you measure the two particles along different directions, chosen at various angles relative to each other, and you tally up the correlations over many trials across many different angle combinations, the two views predict measurably different statistical patterns. If the particles carry hidden instructions, predetermined spins fixed at creation for every possible measurement direction, then the correlations across different angles must obey a certain mathematical limit, a ceiling on how strongly correlated the results can be. This limit is now called Bell's inequality. Any theory in which the particles have definite properties all along, properties that exist independently of measurement and are not influenced by what happens to the distant particle, must respect this limit. The correlations cannot exceed it. Quantum mechanics, on the other hand, predicts correlations that violate this limit, that are stronger than any hidden information theory could ever produce. Here, at last, was a concrete experimental difference. The philosophical question had become a question that could be settled in a laboratory, by measurement, by counting. Bell had transformed a debate about the nature of reality into an experiment with a definite answer. This was an extraordinary turn. For decades, the disagreement between Einstein and the quantum theory had seemed untestable, a matter of metaphysical preference about which reasonable people could differ forever. Bell showed that it was nothing of the kind. The two pictures of reality made different predictions about a measurable quantity, and all that remained was to perform the experiment carefully enough to see which prediction nature actually obeyed. Either the correlations would respect Bell's inequality, vindicating Einstein and confirming that the particles carried hidden instructions all along, or they would violate it, confirming that the particles genuinely have no definite properties until measured, and that the strange non-local character of the quantum world is real. The stakes could hardly have been higher. At issue was whether the universe is, at its foundation, the kind of place where things have definite properties independent of observation, the kind of place our intuition demands, or whether it is something far stranger, a place where properties are genuinely indefinite until a measurement brings them into being, and where entangled particles share a connection that does not diminish with distance. The experiment would take years to perform with sufficient rigor, as physicists worked to close every loophole through which the comforting classical picture might escape. But the result, when it came, would be decisive, and it would tell us something permanent about the kind of world we live in. The experiments began in earnest in the early 1970s and were refined over the following decades into ever more rigorous and loophole-free forms. The first results that drew wide attention came from John Clauser, working with Stuart Friedman in the early 1970s, who built an apparatus to generate pairs of entangled photons and measure their correlations at different angles. The most influential early experiments were performed by Alain Aspect and his colleagues in France in the early 1980s, with refinements that addressed the most serious objections to the earlier work. And over the following decades, as technology improved, Physicists closed loophole after loophole, culminating in experiments around 2015 that were designed specifically to eliminate every remaining way the classical picture might sneak through. The verdict of all this work, accumulated across half a century and many independent laboratories, is unambiguous and beyond reasonable dispute. Bell's inequality is violated. The correlations between entangled particles exceed the limit that any hidden information theory could produce. Einstein's intuition was wrong. The particles do not carry definite predetermined properties hidden from us. Their properties genuinely do not exist until measured, and the correlation between entangled particles is real, non-local, and irreducible. The significance of this result is difficult to overstate, and it deserves to be stated plainly because it is one of the most profound discoveries in the history of physics. The experiments do not merely confirm that quantum mechanics gives the right answers, though they do that. They rule out an entire category of alternative theories permanently. No theory in which particles possess definite properties independent of measurement, properties that travel with them and are not influenced by distant events, can reproduce what is observed in the laboratory. This is not a statement about current quantum theory being the best we have for now. It is a statement about reality itself, established by experiment. The world is not made of objects with definite, locally determined properties waiting to be revealed by measurement. That picture, the picture our entire intuition is built on, the picture of the gloves in the boxes, is simply false as a description of the quantum world. Reality is either non-local, meaning that distant events are connected in ways that classical physics forbids, or it lacks definite properties prior to measurement, or both. There's no longer any room to believe that particles are little objects carrying their attributes around with them, like pebbles carrying their color and weight. The experiments forbid it. It is important to be precise about what entanglement does and does not allow, because the instantaneous correlation across any distance sounds at first as though it should permit faster-than-light communication, which would overturn the theory of relativity. It does not, and understanding why sharpens our grasp of what is really happening. When you measure one of an entangled pair and find spin-up, you know instantly that the distant partner is spin down. But you cannot use this to send a message. The reason is that the result you get on your end is completely random. You have no control over whether your particle comes out up or down. You simply get one or the other unpredictably, with the correlation only becoming apparent later, when the two distant experimenters bring their records together and compare them. The person measuring the distant particle sees nothing unusual on their end either, just a random sequence of ups and downs. It is only when the two lists of results are placed side by side that the perfect correlations appear. Neither party can encode any information into their random outcomes, and so no signal, no usable message passes between them. The correlation is real, but it carries no controllable content, and so it cannot be used to communicate faster than light. Relativity is preserved narrowly by the randomness of quantum measurement. The universe permits this strange connection, but forbids us from exploiting it to send signals, as though nature were enforcing a precise and subtle rule about what kinds of influence are and are not allowed. Still, the connection is genuine, and it forces a deep revision in how we think about the separateness of objects. In classical physics, two objects separated in space are fundamentally independent. Each has its own complete set of properties, and any influence between them must be carried across the intervening space by some physical signal, some force, some particle, traveling at or below the speed of light. The state of the whole is just the combination of the states of the parts. Entanglement breaks this completely. Two entangled particles do not have their own separate complete states. The complete description belongs only to the pair as a whole, and it contains correlations that are not stored in either particle individually. You can know everything there is to know about the joint system and still know nothing about what either particle will do on its own, only how their behaviors are linked. This means that the universe, at its most fundamental level, is not built out of separate independent pieces that happen to interact. It is built, at least in part, out of these irreducible wholes, systems whose complete description cannot be decomposed into descriptions of their parts. The notion that reality is made of separable objects, each existing in its own location with its own properties, is an approximation that holds in our everyday world but fails at the foundation. Separability, like definiteness, is a feature of the surface, not of the depths. Entanglement is not a fragile laboratory curiosity confined to carefully prepared pairs of particles. It is pervasive. Particles become entangled whenever they interact, and given how constantly particles interact, the world is shot through with entanglement at every scale. The reason we do not notice it is the same reason we do not notice quantum superpositions in large objects. The entanglement of any system with its vast and chaotic environment spreads the correlations out across countless particles, diluting them into the general background until they become impossible to track or exploit. This is, in fact, the very same decoherence that destroys the cat's superposition. When a quantum system interacts with its environment, it becomes entangled with that environment, and this entanglement is what carries away the information that distinguishes the system's possibilities, dissolving the clean superposition into ordinary-looking probabilities. Entanglement and decoherence are two faces of the same process. The spreading of quantum correlations into the environment is precisely what makes the quantum strangeness invisible at large scales, hiding the underlying indefiniteness behind a classical-looking surface. The world looks definite and separable not because it fundamentally is, but because the entanglement that would reveal otherwise has leaked into an environment too vast and disordered for us to follow. This pervasiveness has begun to suggest something remarkable to physicists working at the deepest levels of the theory, an idea we will return to in full later, but which is worth planting here. If entanglement is everywhere, if it is the fabric connecting quantum systems throughout the universe, then perhaps it is not merely a curious relationship between particles, but something more fundamental, something from which other features of reality might be built. Some of the most ambitious recent work in theoretical physics explores the possibility that space itself, the very arena in which particles seem to move, might emerge from the pattern of entanglement among more basic quantum constituents. In this view, two regions of space are close together precisely because the quantum systems describing them are highly entangled, and distant because they are weakly entangled. Space would then be a kind of map of entanglement, a structure woven from these connections rather than a fixed stage on which they play out. This is speculative at the frontier of current research and far from established, but it grows directly out of the discovery that entanglement is real, non-local, and ubiquitous, the discovery that Bell made testable and that the experiments confirmed. For now, having established that the quantum world denies us both definiteness and separability, we must return to the question we postponed, the question of what actually happens at the moment of measurement, and confront the strangest of the answers physicists have proposed, the one that takes the wave function with complete seriousness and accepts every consequence, however extraordinary. The measurement problem, recall, comes down to a contradiction between two rules. Schrödinger's equation evolves the wave function smoothly and deterministically, spreading possibilities outward, never selecting among them. Yet every measurement yields a single definite outcome, as if the wave function abruptly collapses to one possibility and discards the rest. The collapse is nowhere in the equation, and the theory does not say when or why it occurs. For decades, the standard response was simply to accept the collapse as a separate rule, to use it because it works, and not to ask too closely what it means. This pragmatic stance, often associated with the physicists centered around Bohr and Copenhagen, and therefore called the Copenhagen interpretation, treats the collapse as a real event triggered by measurement, and draws a line between the quantum system and the classical measuring apparatus, declining to explain exactly where that line falls or what physically constitutes a measurement. It is less an explanation than a decision to stop asking. And for most working physicists, for most of the past century, it was enough because the predictions were never in doubt. But it leaves the central mystery untouched, and to some it has always seemed less like a solution than an agreement to look away. In 1957, a graduate student named Hugh Everett proposed a way out that was breathtaking in its audacity and its simplicity. His idea was to take the wave function and Schrödinger's equation completely seriously, more seriously than anyone had dared, and to ask what follows if the collapse simply does not happen. Suppose there is no special measurement rule, no abrupt collapse, no mysterious line between quantum and classical. Suppose the wave function always evolves smoothly according to Schrödinger's equation, with no exceptions, ever, for atoms and cats and people alike. What would the world be like? At first, this seems to make no sense because we plainly do see definite outcomes. We open the box and find the cat either alive or dead, not a blend. If the wave function never collapses, if both possibilities persist, why do we experience only one? Everett's answer is the part that strains the imagination, and it is also, on close inspection, the most logically straightforward reading of the bare mathematics. If the wave function never collapses, then both outcomes are equally real. Both happen. The cat is alive and the cat is dead, each in its own branch of reality. And the experimenter who opens the box also splits into two, one version seeing a live cat and one version seeing a dead cat, each equally real, each unaware of the other. This is the many worlds interpretation, and it is essential to understand that it is not an additional layer of speculation piled on top of quantum mechanics. It is what you get when you remove the collapse rule and let the wave function do what the equation says it does, nothing more. Consider a measurement in this framework. Before the measurement, the particle is in a superposition, and the measuring device and the experimenter are in definite states. The measuring device interacts with the particle, and because the equation is followed without exception, the device does not collapse the superposition. Instead, the device becomes entangled with the particle, entering a superposition itself, one part of it having measured the first outcome and another part having measured the second. Then, the experimenter looks at the device and becomes entangled in turn, splitting into a superposition of having seen the first result and having seen the second. The superposition does not collapse. It spreads, engulfing the device, the experimenter, the room, eventually the whole world, dividing reality into branches, one for each possible outcome, each branch containing a complete and consistent version of events in which one definite result occurred. Each version of the experimenter is entirely real, entirely conscious, and entirely convinced that a single definite outcome happened, because within any one branch, that is exactly what is observed. The reason you experience only one outcome is that there is now more than one of you, each in a separate branch, each experiencing a different single outcome, and none of them able to perceive the others. The appeal of this interpretation is that it removes the two features of quantum mechanics that physicists find most troubling, the collapse and the randomness in a single stroke. There is no collapse, because the wave function simply keeps evolving smoothly forever. There is no fundamental randomness, because nothing is ever selected, since every outcome happens. The theory becomes entirely deterministic again, governed by Schrödinger's equation alone, with no probabilistic exceptions. The equation that worked perfectly is allowed to apply universally without the awkward second rule grafted onto it. In terms of the mathematics, many worlds is the most economical interpretation, removing rather than adding, taking the formalism at face value, and declining to introduce anything not already present in the equations. The strangeness is moved entirely into the consequence, the vast and unceasing proliferation of parallel branches, but the theory itself becomes simpler, cleaner, more unified. What you pay for this elegance is an ontological extravagance almost beyond comprehension, a reality in which every quantum event splits the world, in which there are countless versions of everything, in which the universe is constantly branching into an unfathomable number of coexisting realities, each as real as the one you currently experience. The objections to many worlds are serious and have been debated intensely since Everett proposed it. The most immediate is the sheer profligacy of the idea, the staggering number of worlds it requires, branching at every quantum interaction throughout all of space and time, an explosion of reality so vast that it offends the principle that we should not multiply entities beyond necessity. Defenders respond that the number of worlds is not really the relevant measure of a theory's economy, that what matters is the simplicity of the laws, and that many worlds has the simplest laws of any interpretation, a single equation with no exceptions. The worlds are not added by hand. They are an unavoidable consequence of taking the equation seriously, and a theory should be judged by its postulates, not by the size of what those postulates imply. A second objection concerns probability. If every outcome happens, in what sense can we say that one outcome is more probable than another? Quantum mechanics makes precise probabilistic predictions, some outcomes far more likely than others, and these predictions are confirmed by experiment. But if all outcomes occur in some branch, the very notion of probability seems to lose its meaning. Why should we expect to find ourselves in the more probable branches rather than the less probable ones, when all branches are equally real? This is a genuine difficulty, and the attempts to resolve it, to recover the familiar probabilities from a theory in which everything happens, are subtle, technical, and not universally accepted. Whether many worlds can fully account for the probabilistic structure of quantum mechanics remains contested. There is something worth pausing on in the structure of this debate because it reveals the peculiar situation physics finds itself in. Many worlds, in the Copenhagen interpretation and the other interpretations we have yet to discuss, all make exactly the same predictions for every experiment. There is no measurement, no observation, no test that could distinguish between them, because they agree completely on what will be observed and differ only on what is really happening beneath the observations. This is a deeply unusual state of affairs in science, where disputes are normally settled by experiment. Here, we have rival accounts of the deepest nature of reality, accounts that disagree about whether there is one world or countless worlds, whether the wave function collapses or never collapses, whether randomness is fundamental or illusory, and yet no possible experiment can tell them apart. They are empirically identical and metaphysically irreconcilable. This forces a question about what physics is for. Is it merely a tool for predicting the outcomes of experiments, in which case the interpretations are idle and we should not care which is true? Or is it an attempt to describe what the world is actually like, in which case the choice among interpretations matters enormously, even though experiment cannot guide it? Physicists are divided on this question itself, and the division runs as deep as any in the field. Many worlds takes the second view to its limit, insisting that the mathematics describes reality and that we must accept whatever reality the mathematics implies, however extravagant. But it is not the only interpretation that takes the mathematics seriously while rejecting the collapse, and there is another path, very different in spirit, that restores determinism not by multiplying worlds, but by adding something beneath the wave function, a hidden layer that Einstein might have found more congenial, though it carries strange consequences of its own. That alternative path was laid out most clearly by David Bohm in 1952, building on an earlier idea of de Broglie that had been set aside for decades. Bohm asked a question that ran against the entire spirit of the standard interpretation. What if particles do have definite positions at all times, just as our intuition insists? And what if the apparent indefiniteness is not a feature of reality itself, but a reflection of our ignorance about those positions? In Bohm's theory, an electron is always a particle, always located at a single definite point, always following a definite trajectory through space. It is never in two places at once, never genuinely spread out. The wave function still exists, and it still evolves according to Schrödinger's equation exactly as before. But in this picture, it plays a different role. It is not the particle itself, not a wave of mere probability, but a real physical field that guides the particle's motion, steering it along its path. For this reason, the theory is often called pilot wave theory, the wave acting as a pilot that directs where the particle goes. This restores determinism completely. In Bohm's theory, if you knew the exact position of every particle and the exact form of the wave function, you could predict the entire future with perfect certainty, just as in classical physics. There is no fundamental randomness. The particle has a definite position, it follows a definite path determined by the guiding wave, and everything is fixed. The reason quantum mechanics appears probabilistic is that we never actually know the precise initial positions of the particles. They are hidden from us, and we can only describe their distribution statistically. When we do, we recover exactly the probabilities that standard quantum mechanics predicts. The randomness is entirely in our ignorance, not in the world, exactly as Einstein had hoped. The wave function does not collapse in Bohm's theory either. It keeps evolving smoothly, but because the particle always has a definite position, we always observe a definite outcome, namely wherever the particle actually is. There is no measurement problem in the usual sense, no mysterious transition from many possibilities to one, because there was only ever one position all along, merely unknown to us until we looked. Consider how Bohm's theory handles the double-slit experiment, because it illuminates both the appeal and the strangeness of the idea. In this picture, each electron is a genuine particle that goes through one slit and only one slit, with a definite path, never splitting, never exploring both openings as a spread-out wave. The intuition that the electron must really go through one slit or the other is fully honored. But the guiding wave, the pilot wave, does pass through both slits, and it does interfere with itself on the far side, forming the pattern of reinforcement and cancellation we have discussed. This interfering wave then steers the particle, pushing it toward the regions where the wave is strong and away from the regions where the wave cancels. So even though each individual electron travels through just one slit along a definite trajectory, the population of electrons is guided by the interfering wave into the banded pattern on the screen. The electron goes through one slit, but its motion is influenced by what is happening at both slits, because the wave that guides it samples both. The interference pattern is recovered, the definiteness of the particle is preserved, and the appearance of wave-particle duality is explained as a real particle riding on a real wave. This sounds like exactly the resolution Einstein wanted, a return to definite particles with hidden positions, the randomness banished into mere ignorance. And in a sense, it is. But Bohm's theory carries a price that Einstein himself would likely have found unacceptable, a price imposed by the very experiments we have already discussed. Recall that Bell's theorem and the experiments confirming it ruled out any theory in which particles carry definite local properties, uninfluenced by distant events. Bohm's theory gives particles definite positions, so how does it survive the verdict of Bell's experiments? It survives by paying the other half of the price. Bohm's theory is explicitly, unavoidably non-local. The guiding wave for a system of many particles depends on the positions of all of them at once, no matter how far apart they are, and a change in the situation of one particle instantaneously affects the motion of the others through the wave, across any distance. The pilot wave links all the particles in a system together in a way that is not limited by the speed of light. This is precisely the spooky action at a distance that Einstein found so objectionable, now built explicitly into the foundations of the theory. Bohm bought back the definite positions that Einstein wanted, but only by accepting the non-locality that Einstein hated. The two things Einstein desired, definiteness and locality, cannot both be had. Bell's theorem guarantees it. Any theory that restores definite properties must surrender locality, and Bohm's theory is the clearest demonstration of that bargain. So we now have at least three distinct pictures of what quantum mechanics is telling us, and they could hardly be more different from one another. In the Copenhagen view, the wave function collapses when a measurement is made. Particles have no definite properties until measured, and randomness is fundamental. But the theory declines to explain what a measurement is or how the collapse occurs. In the many worlds view, the wave function never collapses. Every outcome happens in its own branch. The world is constantly splitting, and determinism is restored at the cost of an unimaginable proliferation of realities. In Bohm's view, particles always have definite positions guided by a real pilot wave. Determinism is restored and the measurement problem dissolves. But the price is an explicit non-locality that connects all particles instantaneously across any distance. Each interpretation purchases its resolution of the quantum mysteries with a different currency. Copenhagen pays with an unexplained collapse and a refusal to describe reality between measurements. Many worlds pays with countless unobservable parallel worlds. Bohm pays with explicit faster-than-light connections woven into the fabric of the theory. And remarkably, as we noted before, all three predict exactly the same results for every experiment ever performed or ever conceivable. They are empirically identical and describe utterly different universes. The existence of these competing interpretations, all equally compatible with every observation, tells us something important and humbling about the state of our knowledge. We possess a theory of extraordinary predictive power, the most precisely confirmed framework in all of science, a theory on which our entire technological civilization rests. And yet we do not know what it means. We cannot say whether there is one world or many, whether the future is fixed or genuinely open, whether the connections between distant particles are real influences or merely correlations, whether the wave function is a physical thing or a mathematical bookkeeping device for our expectations. The mathematics works flawlessly, but the mathematics is silent on the questions that matter most for understanding what kind of universe we inhabit. This is a strange and uncomfortable position for a science to be in, and it has persisted for nearly a century with no sign of resolution. But the interpretational puzzles, deep as they are, concern what happens at the moment of measurement and what lies beneath the wave function. There are other quantum phenomena that do not wait for these questions to be settled, phenomena that operate in the world right now, shaping the behavior of matter and energy in ways that are bizarre yet completely real, measurable, and even useful. One of the strangest of these is the ability of particles to pass through barriers that, by every rule of classical physics, should stop them dead. The phenomenon is called quantum tunneling, and it follows directly from the wave nature of matter, yet its consequences are so counterintuitive that they seem to violate the most basic rules of how objects move. In the everyday world, if you roll a ball toward a hill, whether it gets over the hill depends entirely on whether it has enough energy. Give it a good push and it crests the top and rolls down the other side. Give it too feeble a push and it climbs partway, stops, and rolls back down. It cannot reach the far side without having enough energy to get over the peak. This is simply the conservation of energy, one of the most reliable principles in all of physics. A ball with insufficient energy to surmount a barrier stays on its side of the barrier. There are no exceptions in the classical world. The barrier is a wall, and without enough energy to climb it, the ball remains where it started. In the quantum world, this is not true. A particle approaching a barrier that it does not have enough energy to cross can, with some probability, simply appear on the other side, as though it had passed straight through the wall. It does not go over the top. It does not borrow energy to climb. It penetrates the barrier and emerges beyond it in a region that classical physics declares absolutely forbidden. This is quantum tunneling, and it is not a rare theoretical curiosity. It happens constantly, it is essential to the workings of the universe, and it has been measured and exploited in technologies you use every day. To understand how it is possible, we return once more to the wave function and to the way it describes a particle not as a point with a definite location, but as a wave spread through space, an amplitude of possibility that determines where the particle might be found. When a particle traveling as a wave encounters a barrier, something specific happens to that wave. If the barrier were infinitely high and thick, the wave would be completely reflected and the particle would certainly bounce back. But for a barrier of finite height and finite thickness, the wave does not simply stop at the barrier's edge. It penetrates into the barrier, and inside that forbidden region, it does not abruptly vanish, but instead decays, diminishing in amplitude as it goes deeper. The wave shrinks rapidly within the barrier, falling off steeply, but it does not reach zero instantly. If the barrier is thin enough, the wave, though greatly reduced, still has some non-zero amplitude when it reaches the far side. And since the amplitude of the wave function determines the probability of finding the particle, a non-zero amplitude beyond the barrier means a non-zero probability of finding the particle there, on the other side, having traversed a region it could never classically enter. The particle has tunneled through, It did not climb the barrier or smash through it. The wave that describes its possible locations simply extended through the barrier and out the other side. And so the particle has some chance of being found beyond a wall. It lacked the energy to cross. The probability of tunneling depends sensitively on the thickness and height of the barrier. A thin, low barrier is relatively easy to tunnel through, and the particle has a substantial chance of appearing on the far side. A thick, high barrier suppresses the wave far more severely, and the probability of tunneling becomes vanishingly small, though never exactly zero. This sensitivity is extreme. A small increase in the barrier's thickness can reduce the tunneling probability enormously, which is why tunneling is overwhelmingly a phenomenon of the very small. For a large object facing a macroscopic barrier, the probability of tunneling is so unimaginably tiny that it would never be observed in countless lifetimes of the universe. You will not tunnel through a wall, not because it is impossible in principle, but because the probability is so close to zero as to be meaningless. But for an electron facing a thin barrier just a few atoms thick, tunneling is common, even routine, and it shapes the behavior of matter at the scale where atoms and electrons live. The consequences of this are not abstract. Quantum tunneling is the reason the sun shines, and therefore the reason life on Earth is possible at all. The sun generates its energy by fusing hydrogen nuclei together in its core, building heavier elements and releasing energy in the process. But atomic nuclei are positively charged, and like charges repel. Two hydrogen nuclei approaching each other feel an increasingly strong electrical repulsion, pushing them apart, forming a barrier that must be overcome before they can get close enough to fuse. The remarkable fact is that even in the tremendous heat and pressure of the sun's core, the nuclei do not actually have enough energy to overcome this electrical barrier directly. By the strict accounting of classical physics, the sun should not be able to fuse hydrogen at all. Its core is not hot enough. Fusion happens anyway, because the nuclei tunnel through the repulsive barrier. They approach, they lack the energy to surmount the electrical repulsion, and yet through quantum tunneling, they sometimes find themselves close enough to fuse, passing through the barrier that should have held them apart. Without tunneling, the sun would not shine, the stars would not burn, the heavy elements that make up planets and people would never have been forged. The existence of quantum tunneling is woven into the existence of the universe as we know it, lighting the stars and seeding the cosmos with the elements of life. Tunneling also operates in the technology that fills the modern world. There's a remarkable instrument called the scanning tunneling microscope, which can image individual atoms on a surface, resolving detail finer than any ordinary microscope could ever achieve. It works entirely by tunneling. A fine conducting tip is brought extremely close to a surface, so close that electrons can tunnel across the tiny gap between the tip and the surface, producing a measurable current. Because the tunneling probability is so exquisitely sensitive to the width of the gap, even a change in distance smaller than the size of a single atom produces a large change in the tunneling current. By moving the tip across the surface and monitoring how the current varies, the instrument maps the surface with atomic precision, revealing the individual atoms as bumps in the resulting image. The exquisite sensitivity that makes tunneling seem so fragile is exactly what makes it so useful, turning a strange quantum effect into a tool for seeing the atomic world directly. Tunneling also limits how small we can make the components in computer chips, because when the insulating barriers between parts of a circuit become too thin, electrons begin to tunnel across them, leaking current where none should flow and setting a fundamental constraint on the miniaturization of electronics. The strange quantum leakage that lights the stars also shapes the design of the devices in your pocket. There's a broader lesson in tunneling that connects back to the deepest themes we have been exploring. The classical notion of a barrier, an absolute wall that cannot be crossed without sufficient energy, turns out to be an approximation true enough for large objects, but false at the foundation. At the quantum level, barriers are not absolute. They are regions where a particle is unlikely to be found, but unlikely is not impossible, and the wave function leaks through wherever a barrier is thin enough. The hard edges and impassable walls of the everyday world dissolve, at the smallest scale, into gradients of probability through which matter can seep. This is yet another instance of the central theme that is run through everything we have examined, the way the definite, solid, rule-bound world of our experience emerges from an underlying reality that is fluid, probabilistic, and strange. And it points toward an even deeper strangeness, because if particles can borrow their way through barriers and the vacuum itself can fluctuate, then perhaps the very emptiness between things is not empty at all. Perhaps what we call empty space is itself a quantum object seething with activity, and the next step in understanding the universe is to ask what is really there when there is, apparently, nothing at all.